Good morning, all of you. I'm Kwan Tun Lee from National Taiwan Ocean University. I just checked the temperature in Taipei. Currently it's 24 degrees. So a little uncomfortable for me at this temperature, but the room is quite warm. It's my lecture. Pardon?
Maybe it's global warming effect.
Yeah. Maybe the subtitle of this lecture is a little strange for you, because can we open the black box? So what is the black box, and how can we open it? And what is our knowledge about if we can open this? Is the topic. The magician, instead of a hydrologist or a professor in a university, in fact, I prefer to be a magician. Why? It is all because there's a magician head, the top head. I think all of you know about the magician performance and the rabbit out from the top head. And of course, maybe you complain about all of the magician performance is around a lot of rabbit in his performance. And maybe you prefer a rose and a scarf or a poker card. But we have never known what it will be the next out of the magician hat. Why? It is all because the magician hat is not transparent, and we do not know the detail of the structure, so we cannot predict what would be the next object out of the magician hat. So maybe our watershed, just like this, a black box. We do not have enough knowledge to catch up all the detailed process of hydrologic. So maybe you oppose my opinion because you think we already have a very good skill to do the simulation. But maybe we can discuss for this topic. So the outline of this lecture, we are trying to describe the view of watershed runoff modeling. And we're trying to, from the lump to semi-lump, to distributed runoff modeling, because more knowledge about the watershed rainfall runoff process include in this process. But I think there are, from my point of view, there are still have a problem in selecting Mannings and also because when you want to do distributed runoff modeling, you use the digital elevation model. So that's also the problem. So the view of watershed runoff modeling, we are trying to, previously, all the hydrologic, we are trying to, from this side, to view from this side. So we collect the data, the rainfall data and the runoff data, and then we build up the black box like this. So when we know about the more detailed process, and then we trying to collect the data, watershed size and the shape, stream network structure, overland and the channel flow length and the slope, and the channel cross-section, roughness, land cover, and all the detailed information. And then we think we have enough capability to make a physically best approach. So, but it is true or not? That's my question. So I think all the knowledge system from we collect a lot of data, and when we understand the relation, and then we change from the data to get some information, and then we have knowledge. If we understand the pattern, the relation pattern, and then we have wisdom to understand, to catch up all the principle. So I think the hydrologic process also, we collect the rainfall, discharge, soil land cover, and the watershed topography data, and then we try to bridge the rainfall and the runoff relationship, and the relationship between slope and the runoff, soil land cover, and the relationship with the runoff. And finally, we think that we have enough knowledge, capability to make hydrologic modeling, hydraulic modeling, and we also can do the watershed management because we have a model. So I'm not sure what state we here. Maybe we not enough knowledge to do that. So of course, you think all the first year hydrology course, we know that we have the input precipitation, from the input precipitation to the output, the river discharge, and all the detailed process here. So we know the evaporation, we know the infiltration, we know the evapotranspiration, and we know all the storage. So we think we have enough capability to do the hydrologic modeling. But maybe your knowledge just, for example, evaporation. I think we can catch all the detailed phenomena for evaporation pan. And we also can do all the, we understand all the infiltration process from infiltration plot, a very small scale. But for watershed, that means maybe 100 kilometers square or 1,000 kilometers square. Maybe this link is not so clear. So maybe that's the problem. So we are trying to, from the lump, because we just need to know the rainfall and the runoff, and then we have a simplified function to do this simulation. And when we get more detailed information, we try to do the semi-lump, and finally distribute it. We think, or we hope we can do this thing. So from the lump, the most early hydrologic doing, lump runoff model like unit hydrograph. I think all of you know that we only collect the data, rainfall data, and the runoff data, and then we have this function, unit rainfall and the unit runoff. So the time distribution of this runoff, and then we can use the linear proportional and the linear superposition to estimate the possible outflow at the watershed outlet, and then instantaneous the unit hydrograph, because we don't want to do too much transfer from different duration of the UH, and also the time area measure. If we got a map, and then we can do the simulation, and the linear reservoir is a famous one. So the watershed rainfall runoff process can be simulated by a series of the linear reservoir. Old tank model, I think yesterday we mentioned about this one. And this basically the tank model can be simulated as a linear reservoir model in series or in parallel. So the model like this we can transfer into a series of linear model. So when we want to move from the lump model to a semi-lump, so we hope our model can be derived mainly based on watershed geomorphology characteristic. So we don't rely on the measured data. We may don't have to collect all the detailed discharge data, and then we only based on the watershed geomorphology characteristic, and then we have know all the mechanism. And also we hope our model can be performed with high efficiency, because when you get more mechanism into the model simulation, and you need more time for computation. So that's maybe a problem. If we get more information and then we have a lot of time, and then it may not, this kind of model may not be applicable to for real-time forecasting. So of course we also think because previous lump model is linear, and we hope when we try to modify from lump to semi-lump, we hope we can account for watershed hydrodynamic property. If we can consider about the watershed nonlinear or time variant characteristic. That's we hope. So we move from lump to semi-lump distributed, semi-lump runoff modeling. So I think the first, maybe the earliest one is the U.S. Soil Conservation Service synthetic hydrograph model. And in this, they try to collect more information instead of only just area, watershed area in most of the lump model. So they collect more length, the watershed length, and the slope, and the land cover is a current number. So that's a land cover and the soil type and the antecedent condition of the watershed. So in this case, they have moved from the lump model to semi-lump model. And also Henderson and Wooding in 1964, they trying to separate the watershed into several sub-watershed, and each sub-watershed can be simulated by an overland plane model. So you collect the sub-watershed length and the width and the slope, and then we can build this model, this semi-lumped model. And also the Wooding, they propose a V-shaped model, not only for the, sorry, okay. Ooh. Sorry. Yeah. Okay. Not only for the overland flow, but also have the channel flow. And also, he separated the whole watershed into several sub-watershed. And Weiser transferred the watershed into a convergency overland plane model. And I think the most good one for this for semi-lump model is Rodriguez, Iturbi, Valdez. He proposed a geomorphology-based instantaneous unit hydrograph. Because in this approach, he collects all the detail of the stream network structure, and then in comparison with the previous semi-lump model, he do a very good job approach. So maybe I can use this transparency to show what he have done. For unit rainfall, he assumed this unit rainfall consider n independent raindrop. So for raindrop fall on this the first order overland, and then to the first order stream, second order stream, to third order stream, to the watershed outlet. So for another rainfall particle fall on the second overland flow, second order overland flow, and then second order channel, to the third order channel, to the watershed outlet. So in this third order watershed, all the runoff paths can only be separated as these four different flow paths. That means the first order overland flow to the first order channel, to the second order channel, to the third order channel. And this one is second order overland flow to the second order channel, to the third order channel, to the watershed outlet. So in his approach, we don't want to do the distributed grid-based routing. So in a third order watershed like this, only 4 different flow paths. So you don't need to do a lot of computation. You only do 4 different flow paths routing. So each flow path, we can have a probability of raindrop adopt a specified flow path. And then when we have the probability for raindrop adopt a specified raindrop, and then if we can, we consider the geomorphology characteristic, and then we have the runoff travel time at each runoff state. For the first, we can estimate the runoff travel time for the first order overland flow, and the first order channel, second order channel to third order channel. So we can have this general equation. So after we have this runoff travel time along a specified runoff path, and then we can derive the detail of the watershed geomorphology RUH. Of course, why this we have the probability distribution, because for this as this figure, we can see there are total 7 first order stream, and the first order stream different lengths, different slope, and maybe different, of course, different channel cross section. So if we try to group the first order channel or first order overland flow, and then could be, if possible, we use the probability distribution. And then we can change from the runoff travel time from here to a convolution. This convolution signal. That's the RUH of the watershed geomorphology RUH. So the next problem is how can we precisely estimate the runoff travel time. So previously, I think we already have the runoff travel time for the overland flow. So we consider if we have the overland flow, ice order overland flow length, ice order overland slope, and this the overland flow roughness, and here is the rainfall intensity, and then we have the overland flow travel time for ice order, and then we have derived in 1997. We derived a complicated equation like this, which is we represent the watershed like a C subwatershed, because you can see the C subwatershed is the channel runoff travel time. The channel is collect the data from the overland, both sides overland, and he also collect the data from upstream A subwatershed and B subwatershed. So this equation is more complicated. So this equation can consider the watershed stream network structure. So if we can use like a digital elevation model to extract all the detailed geomorphology characteristic and information, and then we can use this equation to derive the overland flow, the channel flow, runoff travel time, and then we can have the detailed structure of the runoff process from the upstream to midstream to the downstream to the watershed outlet. So we call it the kinematic wave-based RUH model. So this kinematic wave, GRUH, RUH, you know the RUH, and the GRUH, that means the geomorphology RUH. KWGRH means the kinematic wave-based geomorphology RUH model. We have this model in 1997. And so here is the basically structure of the model, because we assume the probability distribution is exponential distribution, which is we usually use in linear reservoir model. So I think because we have another study, we're trying to extract the geomorphology factor from a watershed, to see if the exponential distribution can be adequate to simulate the runoff travel time. So basically, the exponential distribution is good enough for this simulation. So once we have a digital elevation model, and we obtained all the detailed geomorphology factor, like I mentioned about the overland flow length and the slope for different order, and this the channel length and the slope different order. So and the stream network structure of the watershed, and then we can have an analytical solution for this kinematical wave-based GIUH model. So maybe you can see from this figure, because we just mentioned, we hope our model can consider hydrodynamic effect, because we use the kinematic wave. So kinematic wave can consider the rainfall intensity. So in this equation, here is for the overland flow runoff travel time, you can have a rainfall excess intensity. So, and also for the channel, we also have the IE, that means the excess rainfall intensity. So you can see previously for watershed, we only set only one RUH. However, for this model, we have a set of RUH. You can see for the if the rainfall intensity is 100 millimeter per second, and we have a very high peak and a short time to peak. And if we assign a very mild rainfall intensity like 1 millimeter per hour, and then you have a very mild RUH. So in this, we use linear superposition and linear proportional and superposition. But when we derive this RUH, we already consider the nonlinearity of the hydrologic response function. So this is the Hanxi watershed in Taiwan, in the north part of Taiwan, and this the Shijilang watershed in the mid part of Taiwan. And you can see the red one is the RACO, and the green line, the blue line is the model simulation. Basically, I think the model simulation is acceptable. However, in Hanxi watershed, we have the calibrated value for the overland flow roughness is 0.8, acceptable. Channel roughness is 0.05, also good. But for this, you will see the overland flow roughness is only reach such a high value. So you think I think you cannot accept this model. So I think yesterday we mentioned about the model. The model always look perfect because we have a Photoshop. We trying to modify the photo, the picture, and for hydrologic model, we also when this case we just skip up because I think once if I submit our result to an international journal, they cannot accept because of this value. So at that time, in 1997, yes, we skipped this result. I always keep in mind, just Andreas just mentioned about it. I cannot sleep well. So we trying to think the why we need, when we do the simulation, why this roughness coefficient reaches such a high value. It is maybe because of course, the flow velocity is quite slow. So we need a very high roughness value to increase the resistance. So that means to low down the runoff velocity. So maybe it is because the surface runoff is not the dominant effect for this watershed. The subsurface runoff dominates the whole rainfall runoff process in this watershed. So we change our model into a combined V-shaped model. That means because you know the low portion of the watershed, we have a very high groundwater level. So rainfall fall on this region could be a surface runoff. For the rainfall fall on this region could be the subsurface. So we separate our model into two parts. The upper part is for the surface, and the lower part is for the subsurface. So, and we also define a partial contributing area ratio. That means the ratio of the blue length, the overland flow length to the brown one. So this is the partial contributing area ratio. Of course, it depends on at the beginning of the runoff simulation, it depends on the previous, that means the antecedent soil moisture condition. We can count because if we have the rainfall data. And when the rainfall, we got more rainfall on the soil, then this partial contributing area increase gradually. So we do this simulation, and then we change the structure of our rainfall runoff model. So we consider the flow path probability. We have surface flow, and also have the subsurface flow. And the runoff travel time, we consider the surface flow travel time and also the subsurface flow travel time, and also the IUH. We have two IUH, subsurface IUH and the surface IUH. And we assume this can be linear superposition. So this our model structure. We change it from only consider the surface flow, and we further consider the subsurface flow mechanism. So the surface, we just like the previous one, we use the overland flow, use the Henderson and the Wooding equation, and we also find they have derived the equation for the subsurface flow, and also for the we derived in 1997 we have the equation for the channel flow. So after that, you can see the previously this m value, and now down to the 0.6. It is because we have include the hydraulic conductivity in our model. So I think this model parameter value you can accept, and then so we think we have done a physically based approach. Of course, it's just a semi-lump approach. So we make a comparison for the surface and the subsurface flow IUH. You can see it's the total IUH, and this red one is the surface flow IUH, and the purple one is the subsurface. And you can see the recession part of the runoff, of course, is dominated by the subsurface, and the peak is dominated by the surface. I think we only use a semi-lump distributed semi-lump model to simulate all the hydrodynamic effect, and we get I think that we get a very good result. So the rising limb of the IUH is dominated by the surface mechanism, and the recession is dominated by subsurface. So here is the we just mentioned about the partial contributing area. Partial contributing area depends on the previous antecedent moisture and the total rainfall in this watershed. And you can see for the RPCA, the partial contributing area ratio, is equal to 1, and you have a very high peak and a short time to peak. And for a small partial contributing area, then you have a mild peak, a small peak. So basically, I think the phenomena, the physically phenomena has been shown on this approach. And so here's the merit of the KWGIH. We call it a kinematic wave geomorphology IUH approach. So in this approach, we have influence of the rainfall intensity can be considered, and the influence of urbanization change can also be simulated, because in Taiwan we use this because we can consider the runoff coefficient and also the overland flow roughness and the channel flow roughness. When watershed urbanization and the overland flow roughness will decrease, so we can, based on the change of the Mannings and overland flow roughness, and then we can simulate the influence of the runoff hydrograph. And also the flow frequency analysis in engaged area can be performed. We use this for some engaged watershed in Taiwan, because we have long-term rainfall data, and we put all the rainfall data into our model and obtain all the detailed geomorphology factor, use a digital elevation model, and then we can do the simulation. So if we have a 30-year rainfall data, and then we can generate 30-year runoff data, so we can do the runoff simulation. And we have been tested several, many, I think more than 10 watersheds, and then use this model to predict the frequency analysis in engaged watershed. And also because we use linear proportional and linear superposition, so all the computation can be used linear system operation. So we do not need a lot of computing time, and then we can have a real time. We can do the real time forecasting. So this is the model we have done. So this model has been applied to Taiwan, and more than 85 watershed, and basically we have a very good simulation. And also this model has been applied to Russia, because I have an international cooperation project with Dr. Gassman. And also this has been applied to United States, in mainland China, and in India, and Palestine, and Japan, and even one of the hydrologists in Iran wrote a book about the KWGIH and Musli, but I have never met this person. And so the model has been applied, currently has been applied more than 8 countries in the world. And you can see here's the annual rainfall in 2011. In Taiwan, we have a very large annual rainfall. And in Iran, it's only a very small rainfall, annual rainfall. So this model, because we have considered the surface and subsurface, so I think we can have a very good simulation. So the question is, can the semi-lump model will simulate the watershed rainfall runoff process? From my point of view, no. It is all because for this approach we just mentioned, we grouped all the first order stream all the first order overland in a group. So we trying to use a probability distribution to include all the variation, spatial non-uniform distribution of this watershed. So I think maybe if possible, if we have enough computer capability to do a fast computing, and maybe we should move from the semi-lump model to distributed model. So that's what I'm trying to do. So maybe we should reach to the distributed runoff modeling. Of course, all of you know that we can do the dynamic wave model, use based on the digital elevation data set, so fully distributed model. So we can consider the use diffusion wave model, kinematic wave model, or shear model. And all the model input requirement include a very detailed rainfall, runoff, digital topography data, land cover data, and channel cross-sectional data. If you trying to use the distributed model, and the practical problem in use this distributed runoff model is a lot of computing time is required for this runoff simulation. Of course, if you have a supercomputer, maybe you can do this for real-time flood forecasting. But I think we do not have enough amount of supercomputer. So for we want to do the real-time forecasting, flood forecasting, usually we cannot use this kind of model. So if we try to use this, the problem we need to solve is how to increase the computing efficiency. That's what we need to do. So because all the dynamic wave, the diffusion wave, even the kinematic wave, we do not have an analytic solution. So we usually use the numerical, we like a finite difference scheme or finite element scheme to transfer from the partial differential equation to a finite difference equation or finite element equation, and then we can do the calculation for each time step, t plus delta t. So the problem for the distributed runoff routing is how can we and how we determine the value of the delta t, the computing time interval. So that's the big problem. We cannot have, how can we select an adequate one? Because if you trying to select a very small one, and that you need a lot of computing time. But if you trying to use a large delta t, and then maybe you cannot detail describe the wave transport. So we are thinking how to determine the adequate delta t. We hope we can use a large delta t, but instability problem maybe the next one we need to face with. So I think maybe I start here, and the most important one for numerical simulation is trying to use to select an adequate computing time interval. So previously they have two criterion for stability for the numerical instability problem. The first one is the current Friedrich-Lewis condition. So that means the numerical marching speed, that's the delta t divided by the delta x divided by the delta t, must be larger than the wave celerity. And then we can detail describe the moving of the flood wave. So we can use the current restriction equation expressed like this. So in this, we can determine the delta t. And so we use this delta t to avoid numerical instability problem. So this is the first criterion. And the second one is Hunter condition. Hunter condition, that means in flat the mild slope area. For the first time, the water level is higher in the left side, and then we'll move from left side to the right side. And after T plus delta T, and maybe more water move, too much water move from this side to this side. So the water level in next time step is higher. The right side is higher than the left side. So this some water and move from right to the left again. And the T plus 2 delta T, 2 times delta T, and this phenomenon occur again. So that is the water back and forth between two cells. We also call this checkable oscillation. So Hunter derived an equation. That means if we choose this equation, and then we can avoid the overshooting problem. That means the flow reflection between two cells. So we have two limitations when we want to do the finite difference equation. And of course, you want to know what is the exactly value for this delta T when we do a practical rainfall runoff simulation. We use the data from Komarovka watershed. Previously, I think the Komarovka watershed is experimental watershed, and the total watershed area is around 600 kilometers square. It's too large for this test, so we're trying to only use a small subwatershed, Komarovsky. And in this subwatershed, we only have 60 kilometers square. So you can see, because we use this flow hydrograph to demonstrate the second in the second hour is just the beginning of the storm. The 20 hours is the peak time of the storm. So you can see this if the delta T is under the current condition, and you can see the black one is about 20 or 30 seconds. So you can see because the current condition, we consider if the velocity is high. So for the upstream of the stream network, the velocity is quite high. So you can see the current condition, the small time delta T required is just like the stream network. And because at the very beginning, only a little water into the watershed. So there is no flat area. So basically, Hunter condition, all the calculation time is larger than 30 seconds. So at the very beginning, the current condition dominate the delta T, the selection of the computing delta T. So for the 20th hours, so this is the peak time. So you can see the current condition because they have collect a lot of data into the stream network. So in this portion, mass of the selection of the delta T is more than 1 second, only 1 second. And of course, for the Hunter condition, less than maybe 0.001 second. So we need to spend a lot of time for do this computing. So as I just mentioned, we cannot apply, in most of time, we cannot apply this for real-time flood forecasting, except that you use maybe a supercomputer. So this figure to demonstrate this the allowable time step, and this the distance from the upstream to downstream. I'm trying to select a flow path from the first point of the watershed here. And this portion is overland flow, and to the first order channel, to the second order channel, to the third order channel, to the watershed outlet. So you can see that because the downstream channel collect more water, So in this portion, the red one is Hunter condition. Hunter condition, the restriction of the delta T is most of the time it's a Hunter condition dominate this limitation. And for the this portion, almost Hunter and the current condition, the limitation is almost the same. But for the upstream overland, because upstream overland the slope is quite steep, and there's only a small water, so Hunter condition we can have a very large time step. But the current condition, this about the 10 seconds. So maybe this one you can see. This is the downstream part. Downstream part is controlled by the Hunter condition. The midstream part is almost the same for these two constraints. For the upstream part, and it's dominated by the current condition. So of course, once the downstream have a very small time interval required, and all this grid, we need to use a very small time interval. So it results all the computation in most of the period. In a whole a stone simulation, we need to use a very small time interval. So it results in a very a long time for this simulation. So in most of the case, we cannot apply this distributed model for real-time flood forecasting. So so we need to, because we met this equation, this problem. So we are trying to do, if we can do some change, so all this computing time interval can be enlarged. The one is proposed by Mccormick recurrency formulation, which is here is the original the first step is we use the continuous equation to derive the change of the water depth, and then Mccormick proposed an equation like this. This is a little complicated. Maybe I can explain next time, the next PPT. And then once we modify the estimate the water depth from the continuity equation, and then we can use this to momentum equation to derive, to estimate the discharge. So the problem is, what is this? What is this? Maybe we can use this figure to explain, because here is the blue one is the flood wave at the time t, and the red one is the flood wave at the time t plus delta t, moving with c, the flood wave celerity. So at the time t plus delta t, we show the flood wave should move to this place. This is the distance, this is the water depth. And if we choose a large delta t, because Mccormick modified recurrency formula, he tried to modify the water depth because he used enlarged delta t. So when you use enlarged delta t, that means the numerical marching speed is very slow comparatively with the real time flood forecasting, flood transport is slow. So you can see when we use the Mccormick scheme, and we have a green one, green hydrograph. So a green hydrograph is slow than this red, the real hydrograph. So the modification is try to adjust between the deviation of this hydrograph. So he used this kind of equation. So after you use this kind of equation, they can modify the increment of water depth. Use this. But in 1982, Mccormick derived this equation, it can only be used in one dimension. That means when we estimate the blue point, before that we need to have the red point, this term, the red point. So it can be only used in one dimension. So like a river. So we already have this point value, and then come to downstream and step by step. So for our case, we use a digital elevation data set. Basically, this two-dimensional. We usually use calculated from the left corner to the right lower corner. So step by step is this. So if we want to estimate the water depth at this point, of course this flow come to here, and this also. So it's okay, but we do not have, when we calculate at this location, we do not have this value. So the Mccormick recursive formulation cannot be used in this case. So we're trying to remodel this approach. So we cannot, because we cannot use this formulation. So we propose a new sorting skill, the computation sequential. That means if we sorting the water stage of each cell, the value is the water stage at the time t. So you can see this the highest one, and this the second one, third one, and the fourth one. So we sorting this, and this is the first, second, third. So the sorting time is quite limited in comparison with the previous. We choose a very small delta t. So after we do the assign the routing sequence according to the descending order of the water stage, and then we can do the simulation. And also we transfer from the water depth to water stage discharge. So we can do the summation for only because the flow collect from the different direction of the nearby grid. So the another one we need to consider is the Hunter condition. It is fortunate. I think we are lucky because Beth in 2010 he has derived the modified diffusion equation, because previously we used a diffusion wave equation like this. We omit all the inertial term. And he finds that because if we can consider the local acceleration, and then we can avoid the reflux, as we just mentioned, the back and forth, the flux. So we have this equation, and this local acceleration included in the momentum equation can alleviate the checkable oscillation, as we just mentioned. So we integrate all these to modify numerical scheme, and then we can accumulate the inflow discharge step by step. So here is the result. Originally, we may need have a very small time interval, like 0.001. And then now, for the whole process, we can use 60 seconds for all the, from the beginning to the end of the storm flood. So this is our result for the CPU time in minute. The conventional, we need such a time. It's about 30 hours for only 72 hours for the whole watershed, for the whole hydrograph. And then we only use 29 minutes. So in this case, I think that we have solved the problem, because there are two limitations for the computing time interval. The first one is the current condition, and the second one is the Hunter condition. And we integrate all the different modification for the time step, and then we can shorten the computation time from 30 hours to only a very short time limit, half an hour. So, however, have we solved all the problem in runoff simulation? That's the question, the next question. So, I think for the past 25 years, I do research from the lump to semi-lump and distributed, and I trying to solve the problem to shorten the computation time. And but I think there are still a lot of problems I did not solve. Two problems I propose here. The first one is the Manning's roughness coefficient. Because Manning's rough equation, I think that you know about the chassis, the Manning, and the Darcy-Weisbacher. And the Darcy-Weisbacher is more applied in pipe flow. So we have a lot of experimental trying to use different boundary roughness and to describe the flow, the velocity distribution. However, this equation cannot, in most of the time, we do not use it in open channel or string network computation. So we use Mannings. But I think Julian did a very good report to describe what is adequate region for apply a Manning's streaker form, a Manning's streaker. He said only the submerged ratio. What is the submerged ratio? This is the water depth divided by the roughness, the sediment diameter or roughness height. He used the submerged ratio to describe that in this region we can have a good simulation use based on the Manning's equation. However, for this portion is submerged ratio is comparatively small. That means we have a very shallow water depth, and the roughness height, roughness element, the height of the roughness element is large. So this basically is the overland flow region. Okay, so in overland flow region, because you can see this figure, this axis. So in overland flow region, we should have a very high value of roughness. So that means when you do the computation for a whole watershed, you may not can use only one single roughness. Of course, you maybe you say I use a remote sensing map, image map. So you determine a different land cover condition, and then you determine the roughness. But you do not determine or distinguish the watershed runoff, the water depth. So that's the problem. If we can consider the submerged ratio. So what is the submerged ratio? Maybe this figure is more easy to understand. So for deep water, the roughness height is here. So we have a very high water. In this case, the flow resistance is comparatively small. In most of the time, I think we use the open channel hydraulic information from Dr. Winter Chow's book. So the roughness coefficient basically in this region. And however, for the shallow water, I mean the water depth is almost the same size of the roughness height. And in this time, will result a higher resistance. So for the overland flow case, the roughness height is higher than the water depth. So in this case, the element significantly increases the flow resistance. So when we do a watershed like 1 kilometer square, there are a lot of maybe more than 100,000 grid. So how can we determine the spatial variation of roughness coefficient? So we just because we have already do the simulation for the Komarovsky watershed. So here is the water depth. This is the distance from the upstream, as we just mentioned, for the upstream overland flow to the downstream to the watershed outlet. So the water depth from 0.001, of course, this is our computation. It depends on the rainfall intensity, and we can calculate a very small water depth. Okay, maybe it's not true. Maybe just one, okay, you can seek just 1 centimeter, and then reach to the watershed outlet, we have around 807 meter. So the variation of water depth is very large. So if comparison with the last paragraph, and we will consider about how can we determine the roughness coefficient. So you can use this figure. Maybe you think I already have water depth, so I can determine the submerged ratio. But I think basically the water depth depends on the roughness coefficient you have select. So it's not easy to determine based on the already calculated water depth, because the water depth is based on the selected roughness coefficient. So because we use a digital elevation model to determine the flow direction, and then we know the flow accumulation value. What is a flow accumulation value? For this point, because in this point they collect data from collect the water from this and this. So this two grid collect the water from the upstream 2 grid. So here is the total 36 grid. So at this watershed outlet, they collect 35 grid from its upstream. So this we call it a flow accumulation value. So the water depth in the watershed, in the spatial distribution of the watershed, you can use this, the FAV, the flow accumulation value. So once we have this value, because when you do the digital elevation computation, and you have this value, and you have this value, and you can determine the water depth, the distribution of the water depth, and you have the water depth, you can calculate the submerged ratio, and then use the submerged ratio, you determine the runoff variation. So that means we can obtain the spatial distribution of roughness. So this our policy. We trying to consider the spatial distribution of the roughness, so we can more adequate estimate the water depth. So of course we need to, the one thing left is we need to determine the upper level of the, that means the maxima roughness value and the minima roughness value, and this the FAV, flow accumulation value. We assume linear. So like this equation, we once the maxima roughness coefficient and the minima roughness coefficient have been determined, and then we can use this distribution to do all the spatial roughness coefficient determination. So here's the result. We apply this to the Goodwin Creek watershed because it's ongoing research. This research work has not been finished. We apply this concept to Goodwin Creek watershed, and this FAV value, and this Mannings roughness. We have the maxima value and the minimum value, and these two lines. The blue one is from the Mannings roughness from the 0.01 to 0.33, and the red one is 0.07 to 0.30. So we use this to simulate the variation of roughness we use in this water depth simulation. So this is the result of the blue line and the red line, and you can see it's almost the same. So that's the question. But we do not know so far because it is an ongoing approach. We are trying to find what is the best way we to select the maxima of the roughness and the minima of the roughness, and the linear approximation is good enough, or we have another way to trying to determine the spatial distribution of roughness. So this is just a proportion, but we so far we do not know, or we cannot have a very good prediction what is exactly and what is the best way. However, we can see for these two lines, we almost have a very good simulation in comparison with the measured data. So this is the question. So because we just mentioned about the Mannings roughness. For the I think for all the hydrologists think the Mannings roughness coefficient is physically a very clear parameter. However, maybe it's not exact. We know the tendency, but we may not really understand what is the exactly value for our computation. So that's the problem. The first problem I think at this moment I need to solve in the future. And the next problem is we usually use the digital elevation model, because when we do the distributed runoff simulation, we usually use the digital elevation model. So I don't want to spend too much time for this, because I think all of you use a commercial package to handle your digital elevation model. So once you have the digital elevation data set, and then you can do the flow direction determination, depression is flow accumulation value we just mentioned, and we can extract the channel network and the subsurface, and then we can subsurface delineation and obtain. Finally, we obtain the geomorphology factor. So we use a commercial package, or I developed my own digital elevation model to obtain all the detailed information, because as I just mentioned, the KWH model, we need a lot of detailed watershed geomorphology factor based on the stream network structure and different stream order. So if you do the digital elevation model research, and then you will find, because we need to determine, first thing, we need to determine the flow direction. So for a rainfall fall on this part, this is the elevation, maybe it's the elevation data, and you will see you think if we use the steep descent method, that means the the maximum slope, and then the flow, the water will from this direction to here. And if you consider we allow multiple flow direction, and because this elevation is lower than this, and also this one, so they will have 3 direction for the flow. So if you check the previous literature, and you will find they have a D8 measure, multiple D8 measure, D4 measure, D infinity, multiple D infinity. Right? I mean, it's the steep descent we just mentioned from here to here. This is the D8 measure. And if we allow multiple direction, we call it multiple D8 measure. And for this one, we only allow the flow on the cardinal direction, and then we did not allow the flow to the diagonal direction. So this is called default measure. So they allow 1 to 4 flow direction. And if we use a facet, that means the 3 point have a facet. And if we choose the maximum slope of the facet, then we call it D infinity. If we allow 2 maximum slope for the facet, and then we call multiple D infinity. So in this case, you will see this one should be the flow direction is the most concentrated one, and this one should be the flow direction is the dispersive one, the most dispersive one. So we have this result. This is the number of flow direction. This is the number of flow direction, and the area percentage. So the D8 measure, we all the flow direction concentrate only one direction, and the multiple D8 direction measure, we have a dispersive phenomena. So I think maybe you can expect a result like this. We have a very concentrated one and a very dispersive one. You can see this portion. In original, in D8 measure, we do not have this portion. And moreover, and the string network structure is not the similar with this one. So that's the question. What is the exactly the best way to simulate, to extract the string network or the watershed boundary, the string network and the watershed boundary? What is the real one? This one or this one? And of course, only just you see this figure, you do not have exact value. So if we have a value like this, so we're trying to find the longest flow path from this way to this way. We find that drainage path is about 8,000 meters. And for this case, for the most dispersive one, we have more than almost two times. So you know the longest flow path, we usually use this geomorphology factor to estimate the travel time or the time of concentration. And then we use this time of concentration to maybe like a SCS triangle unit hydrograph measure to estimate the time to peak and the peak discharge. So if the deviation is quite large, the difference is quite large. So what is exactly the one should be most similar with the real watershed? That's the question. So we also have the width function. I think maybe you know that width function. Width function just like we call it a hydrologic response function, or maybe the IUH unit hydrograph or instantaneous unit hydrograph, because we count the link. The number of link for a given distance from the watershed to the watershed outlet. So you can see, basically, I think you can think this is a hydrologic response function of the watershed. And this the hydrologic response function we use the dA method, derived from the dA method, and this is the multiple dA method. So you can see the centroid of the width function should be here, and this one, the centroid of the the width function should be here. So if you use a different flow direction method to obtain the width function or obtain the longest flow path, and then you will have a quite different approach, and you get a different result for your hydrologic simulation. So can we trust the digital elevation result? So totally, I think the first one, as I propose, the Mannings end, we do not have a very good approach, and have a deterministic. We can obtain the exactly what should be the exact value of the Manning end, and the second one is what is the best way for the digital elevation data set for the geomorphology factor extraction. Of course, if you use a commercial one, the commercial one is usually use D8 method. So but in reality, what is the real condition in watershed? That's the problem. So a short summary and a remark. This which I just mentioned in this lecture, and in the lump and semi-lump, I think that we use a simplified lump structure for runoff simulation. So previously, different people try to use different concept to obtain. Of course, it includes kinematic wave-based geomorphology, RUH. We're trying to obtain all the detail geomorphology factor of the watershed to build up our RUH model. So basically, we can use a map or the digital elevation data set, or from the, of course, include the land cover condition, and then we have this model, this kind of model. And because we only need a little time for computation, so it is adequate for real-time flood forecasting. On the contrary, when we use the grid-based distributed model, we can consider the spatial variation of the watershed characteristic. So, in my opinion, if you do the watershed resources, water resources design, maybe you can use this model, but it may not be applicable for real-time flood forecasting. And the problem in selecting the Mannings roughness coefficient, I think the phenomena, of course, you previously, I think everyone think because we have a standard table for the selection of Mannings roughness, but actually the Mannings roughness should be depends on the water depth. So we may not can use a single table to determine the Mannings roughness. So I think this is a very big problem, because the physical, when we want to develop a fully physical based model, seems to impossible at this moment. If we think the Mannings end depends on the water depth. So that's the problem. So the problem in use digital elevation model, we propose, we make comparison for the previous totally 5 different flow direction determination. And we find that the D8 method generates the smallest watershed area and the shortest flow path. That means currently, if you use a commercial package, your watershed is the smallest one, and your longest flow direction path is the shortest one. So when you use the multiple D8 method, you will get a bigger watershed area, and maybe 1.5 times to the original one. So the scale of the uncertainty in using the digital elevation model is hard to be clearly defined, because your digital elevation data set, you got different resolution of digital elevation data set. And of course, the vertical resolution is also influenced the final define of the flow direction. So that's the problem. We currently we cannot really understand the range of the uncertainty in using the digital elevation model. So I think this all my research, and I hope I can obtain some discussion with you, and because a lot of topic it is still unsolved, ongoing research. Thank you very much. Any question?
You show your conclusions that this previous.
This one?
No. This one.
Oh.
Your second point.
Yeah.
Do you think there is some contradiction in this conclusion? Because if you have any territory and say 10 watersheds, 10 outlets and 10 watersheds, if you say the A method provides the smallest watershed,
Yes.
another watershed should be large.
No,
bigger.
no.
Because all the territory should be covered by 10. So you consider only one watershed is smallest, but all the territory is covered by the same number of watersheds.
In fact, in this case, we have used a different watershed digital elevation model data set. And the ratio of the watershed area derived by DA and the multiple DA is different. However, the DA method is always obtain the smallest one. It's quite, I think it's always like this. But the ratio is a little different. It depends on the resolution of digital elevation data set, and of course the vertical resolution is also controlled as the most important one for the flow direction. So the vertical direction and the horizontal resolution is the most important one. But I think the DA method is always the smallest one.
I mean, if you have one watershed smallest with DA method, some neighboring watershed should be bigger. So you understand?
Okay.
All the territory should be covered.
Okay. Your concept is based on the watershed boundary. It's very clear. However, as we see in this case, so the watershed boundary for another one should not maybe overlap. Yeah, because the flow is only part of the flow to another region. So, but we think, so yeah, you are right. The neighbor watershed may overlap this one, because some water from another watershed flow to here. only a portion, not hold the whole water from the grid. So they will be overlapped.
Some territories could be included in different watersheds.
Yeah.
I see. Nice conclusion.
Yep.
I like the discussion about like chemical for slide when you compare mine roughness to formulation water graphic. It's really far back. Graphic about like main roughness out of
Okay.
And on the previous one, yeah, this one.
Oh, this one?
Yeah. How can you compare flow accumulation value to what this? Because like if you're gonna work with raster or particular elevation model, so flow accumulation value will be like the same every time when you just working with this raster when water depth changing time from the time because of the.
Okay. Flow accumulation value is not the real watershed. This is just the tendency of the water depth.
Yeah.
So this is always, in my case, in this case, it's always the same. The spatial distribution of flow accumulation is always the same. So I use this to determine, once I have the make an assumption for the maxima, make the assumption for the maxima roughness coefficient and the minimal roughness coefficient, and then I have all the grid, the roughness coefficient, the spatial distribution of roughness coefficient. So this will not change from time to time. Yeah. For the whole stone period, it's almost the keep constant. It always keep constant. So it's the lunchtime. Yeah.
The Mannings coefficient is not constant. It depends on flow depth.
Yes.
Which is another issue of uncertainty in the world.
Yeah, I think the previous the Julian result is very good result, but he did not propose the solution. He just proposed a question. So I'm trying to give a possible result for the simulation, the spatial distribution of the roughness coefficient. Yeah. Okay.
I'm sorry, it's a little naive question because I'm not much of a hydrologist. We have this experimental catchment of ours. I used to run it when I was around. So I know it for 22 years. So in 22 years, I've been a lot on the field. I've seen twice water running on the ground. Once was last year. There was a huge flood in the Paris area, and the other was in a very cold winter. There was a rain on some frozen ground. So I saw it twice. So I don't want to make probabilities, but it seems to me that in some area of the world, water running on the ground and that can be approximated the way you show it is very rare. Of course, I'm sure that with the rainfall intensity you have in Taiwan is not the case. But what do we do for the rest of the world? Does it still make sense to try a kinetic approximation for water that is flowing somewhere else?
Yeah. Okay. The case in Taiwan, the rainfall intensity about 1.1 return period, we can reach to about 30 millimeter per hour. So in that case, even in the upstream watershed, we can have a surface runoff. But of course, it depends on the land cover condition and the soil. But in Taiwan, the rainfall intensity is quite large. So So it also have I have the chance to distinguish the different flow mechanism and to modify my model. Yeah. Yep, I think this open question. Yeah, thank you.
Okay, lunchtime. Thank you very much again.